3.
Okay. I think I made one with 5 and 3 before.
Do you want a different number?
Yeah.
Okay.
How about 4?
Let's do 4. I was thinking of 4.
Really?
Yeah, well.
I can do that.
Because we said 5 and 3, so I thought of 4.
20. This is gonna be.
Some big numbers.
Yeah, the numbers are gonna get big. This is like gonna be. What is this? It's like gonna be. I think it's.
5 and
I
20
think it's
and
like
80.
This is gonna be 320.
Really?
The numbers are gonna get.
You're doing
big.
those all in your head, aren't you?
Yeah. Eventually, I'll need a calculator.
Should I guess the next number? Maybe 1280.
Let me see. I don't want to do that. No. Just get rid of this. Get rid of that.
Is my calculator causing trouble?
Yeah.
Okay. I can turn it sideways. It might be easier.
It is sideways.
Oh, I'm sorry. You're right. I meant sideways of sideways, so up and down. Let's see what you got.
Yeah.
It is 1280.
Yeah. Let me just write down the rest of the numbers.
Okay.
Because these numbers are gonna get big. You may already see what I'm doing.
I kind of do, I think.
You'll see why I'm doing this.
Okay.
I'm not just writing down this whole thing for no reason. Let's see. What?
Look at that. 20480. Yes, that's right.
I'm just.
Is this going to be a magic square?
It's gonna be something like a magic square.
Okay. Really? And are you putting them in a special place, or are you just putting them anywhere you feel like putting them?
You'll see
I'll
how
see.
I'm putting them.
Okay. Yeah. Wow. Big numbers.
Yeah. These numbers get kind of big.
I see that.
This is gonna be huge.
This is a big one. 327680.
There we go.
There we go.
Now, let me show you. Let me show you what's so great about this.
Yeah.
Since I use a calculator, I don't need to check because I already know it's true. So if you multiply these numbers, it's almost like a magic square, except it's with multiplication.
I'm going to multiply all the numbers in that row?
Yeah, if you multiply these, it's the same.
Should I do it?
Yeah,
or you want to do it? Okay, I'll try
Just
it.
check it.
All right, let's do it.
Just
So I'm supposed to multiply this times this times this?
And this times this and
Okay.
see if they're all the same.
I can't
Multiply all
believe
the
it.
rows, columns.
That's
and
hard to
both the
believe.
diagonals.
You discovered this yourself?
Yeah.
Wait a minute. Times 5 times 5120. It's this gigantic number.
Oh wow.
2.09. Do you know this thing? E9?
Yeah. It's just times 10 to the 9.
Beautiful. Right. So should we write it down or not?
I could. I don't often do that.
Okay. 2.097. It's okay. We're not. I'll do it.
Yeah, you can do it.
2.097. 152 times 10 to the 9th, which another name for that is
a billion.
a billion. Good. Right. Okay. So it's a little more than 2 billion.
Yeah.
All right. Now, the next one, is it really going to work? 80 times 1280 equals that number, but then times
this monster.
This monster equals oh, get out.
Now try this one.
Really? Get out of here. It's going to keep working? Okay. I'm going to say same.
I hope so. I hope
I
it'll
hope
work.
so, too.
Well, something will be wrong.
Something's wrong with my calculator.
I'm using your calculator.
Could be a wrong calculator.
Yeah.
Let's see if the calculator is working correctly today. 680 equals that big monster. But we're not done because I still have to go times 20 equals, all right, hold your breath. Yay. And again, wow, that's a very cool thing.
Try all
Oh,
the
no, you're kidding.
Yeah, also all the columns should do the same
What?
thing. And also both the diagonals.
No.
Yeah,
Really?
yeah, I'll tell you why.
Why?
Oh, that's interesting. Oh, wow.
It's like gonna be.
Wow, really? This is a great thing you discovered. Okay, I'm gonna do.
8, 1, 9.
Let's do this diagonal here.
Yeah.
That
Then
one looks.
then also try the.
8, 1, 9, 2, 0 times 1280
Times 20.
times 20. Oh man. Wow, you really discovered a whole new magic square thingy.
And also try this diagonal.
But why does it work?
Yeah.
It's a like it's a I'm not just putting these numbers in random places.
No.
And also
I wasn't even watching what you did. You were careful and I didn't. Do you always start here?
Yes.
Yeah.
In this kind of one.
You always go here and then here.
That's because you go like this. Well, since it doesn't go there, so you just go there. I kind of memorized all of them because I kind of memorized all of them. Go here, here, here. Also, if you haven't memorized,
Really? Let's see. If you go here, here, here.
then you go there. Then you let me show you how you do it.
Yeah,
And so,
show me the path.
And so pretend this is all blank,
Okay.
and you have 4 around it. To make it, let's first talk about how you make an adding magic square, where all the rows, columns, and both the diagonals add up to the same number.
Okay.
And so like that, you go up here, you land in this square, which would be this. So you go in that one, and then since again it happens, so you go there, and if you run into a number, you just go down and you keep on doing that, and then you just finish it.
That's how you do an adding magic square?
And you need to just add a constant.
Can you do one for me, just so I could see it?
Yeah.
I don't really know
Let me
about
do
this.
the classic one.
What's the one that adds up to 15?
Yeah, that's the classic one.
Okay.
This is one.
Oh, I have to watch carefully what you're doing.
That's the classic one.
It is, huh?
Does look. In this
I
case,
see.
you add 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1.
Yes.
It's a, and here,
Yeah.
it's so that's how you do.
Hey, yours is just following that same pattern, but with multiplying.
You'll see why.
You went 5 and then times 4, and then you went to
let me-
number 3 position.
Yeah. Let me.
Oh, you're following the classic one.
Kind
of, except it's now multiplying.
Let me show you how I came up with that.
Yeah, how did you come up with it?
And so say
This is good.
a way of doing.
Should we show for the record what's going on here?
Yeah. This is the multiplying and this is the classic.
This is clever. This is so clever.
And so you a way of turning this into a multiplying magic square is just raise some number to the power of all of these. Say like 2. This can be 2 to the 8, 2 to the 1, 2 to the 6, 2 to the blah, blah, blah.
Oh, okay.
Because then the powers just add up to the same thing. So they multiply to the same
That's
thing.
clever.
And another way is you so say you have natural logs in here.
Oh.
When you add natural logs, you just do that thing with multiplying.
Yeah.
You can raise e to the power of them. So then you get a multiplying magic square. Let me show one.
Oh.
Yeah. This is what I'm doing. So A, then it goes A, B. This is what I'm doing. See, this is it. Now do you see what I'm doing?
I do. You're doing
See?
AB squared over there.
Then AB cubed.
Beautiful.
See that?
Wow.
And then you just go,
And
keep
then,
on going. And then you got this. In this case,
Oh, I
5
see. And this is
A.
like AB. Wait, AB to the 0.
I
Kind of, but It's interesting. It feels more general than a magic square because you did, well, I mean, because the A. Is there a magic square that starts with 0? Is that kind of like what you did? It is. It's almost like starting with 0 and you subtracted 1 from everything.
Yeah. Then this would be 0 and this would be 1. This would
right.
be 2.
So that's kind of what you did.
Yeah.
This is like AB to the 0 and AB to the first.
Yeah. Then AB
squared.
Yeah.
Is your last one AB to the 7th? I bet it is. Sure,
it
would be because that's the biggest one.
This is going to be AB to the 9.
Really?
Yeah, because look,
Oh,
this
there's
is
9. AB to the 8th is down there, the big one, right? Okay, yeah. Okay.
And so this is the...
Oh, yeah, right, because there's 9 entries. Right,
Yeah.
9 entries.
And this is the
good.
last one. It goes... Boop,
AB to the 8th
it
is
goes
the last
boop,
one.
boop, 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 boop.
Wow, so you're making it work.
That's how
That's clever.
I just happened to come across this.
That's so clever. I like
I
it.
didn't find it.
Really?
I didn't find any of this in a video.
No.
But I did kind of learn the adding thing. Even you. First, she looked it up.
Even I could
Even
do it.
Mom.
Yeah, she
Even Mom
looked
was
it
a
up
professor.
and then
Professor at an Ivy League school.
then she
Even she understood that.
she looked it up and then she taught me and then that was a long time ago.
Uh-huh.
And then I just
When you
came
were
across
young, right? When you were a kid.
And then I just came across this. Do you want to
That's
check
tremendous.
the other bits?
Yeah. I would like to check.
To test if your calculator
A
is...
calculator might not know how to do them all. I mean, this one looks like it might not work. I think, of course, it will work. I know.
Yeah.
But I'm just gonna try it out for the
Unless
pleasure
your
of it.
calculator doesn't work.
All right. Sometimes they get tired from having all the
Good to
electricity.
have confidence in your...
Yeah. Times 1280 times 5120. Bang. It's just great. It really works.
Uh-huh.
That's
Wait, you didn't
really
try
nice.
all the columns.
No.
Well, but then you will run out of time for other questions.
Yeah, we could do
Yeah.
other things. I believe you. I can see why it will keep working.
Yeah.
Yeah, it's great. And your argument really explains it.
Uh-huh.
And it's so clever that it works with any A and B.
Yeah.
What numbers are better? Do you normally use smaller numbers like 5 and 2 or 2
Yeah.
and 3?
Or else look at... This is already a monster. It's so... And that's also why I do a 3x3. If I did like... Because using this trick, it works for odd numbers by odd numbers. Because the adding trick works for odd numbers by odd numbers. Like it's a like 5x5, 7x7.
Oh, yeah.
And the smaller one will just be a 1x1, but that's boring.
That's a funny case.
Yeah.
1 by 1. What about if there are negative numbers? Like if I had said 5 and -1 or something.
Yeah,
Would it
that
still,
would still
it'll still work?
Yeah, it still works.
That would be even more surprising, I think.
Yeah.
But it looks like
And
it would still work.
I also, once I actually put imaginary numbers in.
Really?
And I multiply by I.
Oh,
But
cool.
and also it looked kind of weird, cause like they repeated every 4 numbers.
Ah.
Cause like I did a fourth one.
Oh, yeah. Great idea. That's a great idea.
But that's a bit harder to check.
Do you want to hear something funny about I?
What?
When I first learned about I asked my teacher, what if I raise I to the I power? What would that equal?
It would be like cosine pi I over 2. No, cosine natural log of pi over 2 plus I sine plus I sine natural log of pi over 2. That's gonna be it.
Really?
Yeah.
Wait, what?
Let
You did
me
it so
write
fast. Write it down for me.
Let me show it to you.
I thought I was going to give you something to think about. You
yeah.
just gave me an answer right away.
Here we go.
My teacher didn't know how to do it.
Right?
Let's see what you...
I can explain why.
Yeah, show me
this
what you're
is-
doing. I to
and
the
so,
I.
if your teacher thought about it, they probably would
Well,
be able.
I don't think he knew.
I to the I.
See, I don't think he knew this
equals
thing that you know about E and cosine and stuff.
Cosine.
So what did you do there? You said I is E to the I pi over 2 or something?
Cosine natural log.
You're just writing the answer straight down?
Are you going to explain it?
I'll explain it.
Yeah,
I'm just gonna write it down.
Okay, tell the answer first.
Okay.
If you see it already.
Let me just.
Don't
That's
worry
not
if
it.
you're skipping
This is
steps.
it.
Cosine of pi I over 2.
This is kind of imaginary number.
Well, that's what I'm wondering.
Plus I. This is also pi I. And there we go. That's the answer.
Really?
Let me show you why. Say you have x to the I.
Yeah.
That equals e to the power of natural log of x times I. Right.
That's good. All raised to the I power, right?
Yeah, times I.
Yeah.
Right. That's
Yep.
it.
Yep.
And e to the I theta equals that equals this thing because it's like gonna be cosine natural log of I plus I sine natural log of I and natural log of I, since e to the pi I is -1, then e to the pi I over 2 is gonna be I.
That's right.
And so that's how I got this.
I'm a little worried about it though. It doesn't look exactly like what I thought it was going to come out.
What did you think it would look
Well,
like?
I thought I would go I. This I
Yeah.
is e to the I pi over 2,
Yeah.
which we're all okay with that, right? And then if I do all of that to the I power,
Oh yeah.
I mean,
Oh yeah, you multiply by I. It would
right.
be like e.
So then it could be, that would be like e to the I squared would be negative pi over 2.
That's another answer. That's another answer.
That could be an answer, but except there's more answers. That's the interesting thing because
that's an answer, but also this is an answer
Really?
too.
I'm a little nervous about that. Really? Let's see. So
This is just
because there are many answers. Actually, there's infinitely many answers. But maybe yours is another one. But let's see. What did you do? So you said
it's like this is going to be
this is
cosine
log.
This is cosine natural log of x plus I sine natural log of x. Right.
I'm trying to understand. You made this. Wait, did we not do it the same way? You said x, which was I.
But then and since
Oh, and that's a times. I see. It's log x times I.
Yeah, and if you take e to the I theta, that equals just cosine theta plus I sine theta, and here theta is natural log of x. So and natural log of I is pi I over 2.
Well, that's the interesting question. What is the natural log of I?
Yeah, it's kind of easy if you know that.
So you said it should just be pi over 2?
No, pi I over 2.
Pi I over 2, thank you. Much better. Yeah. So that's one possible answer. But the other thing is, I, which in the complex plane is here, could also be, this angle could be pi over 2, but it could also be pi over 2 plus another whole 2 pi. Did you ever think about that? It could also be 2 pi plus pi over 2 times I, because that's the same angle.
Yeah, that's the same thing.
So
but this is the same thing, except it's...
Well, so it could be pi over 2, but it could also be pi over 2 plus 2 pi all times I. It's a funny thing. There are infinitely many answers
and so
for
that
this.
You could also put this into here. And it would still be the same thing, and you could also do it again and again.
Really? I have to think about that.
And that would be, it should be the same thing.
Interesting. I'll have to think about that.
Unless Euler's wrong.
No, he's not wrong. Euler was one of the first people to think about log of I.
Yeah, he is right. I've seen its proof.
Right. He's right about that.
And so there must be infinitely many values
of I to the I.
Yeah. That you can just plug it into here.
So maybe.
It makes sense that.
I'll let you think about it some more when you go home. It's an interesting old question.
Yeah. And so since it's also these answers, you could also say it's cosine pi over 2 plus 2 pi I plus I sine that thing.
Yeah.
Or you could also do 4 pi.
Exactly, right.
And so
That's what people do. They go pi over 2 plus any number of 2 pi's. 2 pi
That's
times any k, or that's
or
any
2 pi
integer.
n.
Or n if you want to call it n. Yeah. Right, where n could be any integer. 0, plus or minus 1, whatever. So yeah. Nice. Wow. So that's already college complex variables that you seem to know how to do, or at least the beginning of it. Yeah. Good.
And do you I'm just saying you might you probably do know about the gamma function. You might not.
I do.
Okay.
I do. But I didn't think of it myself. Someone taught me. You read
yeah.
about it somewhere?
There's
That's
like
great.
this rule about the gamma.
Where are you reading about that? What books?
I heard of the gamma.
Or on TV?
I actually
on YouTube?
looked it up.
Really?
With my dad.
Guess who thought of the gamma function?
Yeah, I was thinking
Do you know
about
who invented it?
factorials of not whole numbers.
Right.
And that includes the gamma function.
It does, exactly.
And so that's
You did ask us what is the
I think it's
factorial
Euler. I think Euler might have invented
non-whole
the gamma.
numbers, and neither
great
of
question.
us knew the answer.
Really?
Yeah.
It's a very
So,
nice question. It's
yeah.
like connecting the dots
Yeah.
on the factorial. Yeah, Euler
I
figured
actually
that
made
out.
a factorial graph on my own calculator, and I
Oh.
managed to get rid of the negative number factorial, which is just all crazy.
Really?
Yeah.
That's
Because
interesting.
negative n factorial is minus 1 to the n divided by n factorial. And so it's going all kind of crazy over there. So I just did the absolute value of x factorial, and then I just ignored the other part. So then I got an x factorial.
Yeah.
Without the.
There's also a funny thing when you do factorials that there's a minimum. If you do the gamma function has a funny minimum value somewhere that I'm not remembering. Should we look at a picture of it?
We could, yeah.
What if we ask,
We
do you
could
use Wolfram
figure-
Alpha or anything like that?
Oh yeah, I would have Wolfram Alpha.
Or Mathematica? That would be
We
fun
haven't
for
looked
you,
at
right?
Mathematica much, no.
You don't use that? Okay. What if we
We've
just ask,
done like MATLAB and some of the more kind of
what if we
based on
just
type.
go to Wolfram Alpha and see what he does for us? There's Wolfram Alpha. I think, what if I say graph? What if I say graph
The gamma function.
gamma?
It's
There it is, graph gamma function. It's built in. Let's see what it does.
Let's see.
There. See that interesting thing? It comes down and then it has a minimum somewhere and then starts going up again. And that's an interesting question.
Or
Where's
we
the
could
smallest?
take the derivative and double derivative
Good
and do
idea.
the quadratic.
Let's do that.
Yeah,
Let's do graph the derivative of the gamma function. Let's see if it can do that. It did. And now, do you
what
want to
is
know
it?
where it
This
equals
is-
0, right?
Yeah, I want to know.
So
where it
let's
equals
see,
0.
when is the, let's ask it that question. Where is the derivative? What do you think, how should we ask it?
When is the derivative equal to 0?
Let's do it like that. Because it looked, where did it look like? Somewhere around 2 or something?
I don't know.
Oh, a lot of places. Wait,
Oh.
no.
Huh?
What's it doing?
I don't know.
It's giving a lot of funny numbers. It said
It's like
a
negative.
bunch of negative numbers. I wanted to know the first positive one. This one, that
Here,
one.
1.46 about.
Let's see if that's right. 1.46. If I go back, do we think that looks reasonable, right?
Yeah.
Somewhere between 1 and 2. It's crossing through 0. Oh, I see. Because it's also zeros over.
Oh yeah, because it doesn't cross.
So is that right? Why is that? So
let's
what's the
see.
gamma for negative numbers?
Um,
Oh, because it has those things,
Yeah.
flat places like that.
It's a, like it's.
Isn't
So
that
it's like
interesting?
1.
Oh, there it is. Has a bunch of.
And so that means it has like that means it like has a ton of minimums.
Isn't that so interesting? It does.
Yeah.
It has a ton of places where it's got a zero slope.
Yeah.
Minimum and maximum. Like there's a local maximum in this
Yeah.
one.
Uh-huh.
Wow.
Uh-huh.
You're ready to do a lot of
It's-
math, I see.
Or we can, and we can also figure out what the double derivative
This is pretty unbelievable.
and figure out when it's positive and when it's negative. And then we get when it's.
Good, because you wanted to see the minimum or the maximum with
Yeah.
the second derivative test. That's a good
Or we
idea.
could just eyeball it.
You could.
Um,
It's good to be just
I don't know.
eyeballing like that, yeah.
it's kind of, but that's
Well, it
fine.
looks like we've got a minimum, then a maximum,
Yeah.
then a
But
minimum.
it looks like about 2.
This one over here?
Yeah, that one over there.
Yeah.
Like 2. Or maybe we could just take the double derivative.
Let's ask graph gamma function from x equals 1 to 3. How about that?
Okay.
And then we'll see what that does. Does it know how? Yes,
Yeah.
it did it. And then, so we think it's got its minimum. It really thought it was at 1.4 something?
1.46.
Really? How about from 1 to
6 or something.
1.6? Okay, let's see if we can still see it. I mean, this is a very slow way to find a minimum. You can just make it do that kind of thing.
Yeah. I
Yeah, it looks like it's working. What if
Yeah,
we go,
it's kind of going down.
how about from 1.4 to 1.5? Let's see if we can zoom in like that. We can do this more efficiently, but because it thinks 1.46. It does look pretty reasonable now when you see
Yeah.
1.46. So yeah, that's a famous minimum of the gamma function. And I don't know what that number is exactly. I mean, is it something in
It's
terms
like
of
one-
E or
Yeah.
pi or something
I
like
know.
that?
Like if you I only know the Riemann zeta function of 3 like just as its decimal. I don't know like
Right.
how you in terms as
I'm gonna
pi
ask. Let's see if we ask for an exact formula for the minimum of the gamma function.
or
I have no idea if there's, and I'm not kidding, I don't know.
yeah.
What is there? I don't think there is, but maybe there is.
Maybe
Let's see.
there's a formula for a lot of stuff.
That's right, sometimes there is.
Like
Minimum of gamma function. Do you ever know this thing, stack exchange? You might like stack exchange.
Yeah,
There's a
I
lot
know
of
about-
math
yeah,
on stack
yeah.
exchange.
So Zameer has learnt a lot of
There
math
is.
and he can't do as much in programming
Yeah.
as he can think about math. So he's been
Oh,
less
go
reluctant
up a
in,
bit.
in
Go up.
programming.
See that one?
That's a great formula, isn't it?
Yeah, I think I saw that one before. But
That's
I
a
saw
famous
different
formula,
one.
yeah.
I saw a different one. I saw like I saw one for like all the decimals. Like if you have some number that's a decimal, then the gamma of that decimal times the gamma of 1 minus that decimal equals pi over sine
That's
pi times that decimal.
right, that's that thing you're remembering. That's it.
But this is kind of different.
Wait, that's someone wrote a wrong formula. Oh no.
That's kind of
Wait, how can this formula make sense? Why does it say x? This side doesn't even have x.
yeah. What is
Someone
that?
wrote something wrong.
Yeah.
What do they mean?
Does
I
it
don't know
say-
what they mean.
It's a,
Someone wrote the wrong formula.
yeah.
Maybe they
It's
meant.
supposed to be like x.
What do they
gamma
mean?
of, I don't know. Where did that x come from? Is that x supposed to be pi?
That x
Then-
doesn't make any sense.
Yeah.
Maybe is it pi?
and-
Yeah, I don't know.
Yeah. Then why did they write pi up there?
I
They
don't
could have
know.
just write x.
Yeah.
Someone
So maybe
copied
you
it.
can do your first bug report.
That's a bug report.
It's supposed to be 1 minus p, not p minus 1.
Maybe so. Something is really messed up.
Yeah.
Something's really messed up
You
there.
should tell this person
Yeah.
their formulas.
Maybe someone below corrected.
Um,
It says edit. Did someone correct them? No.
Probably not.
They should.
Yeah.
There's the 1.46 they found.
Yeah.
But still, I have confirmed it is not possible to find the gamma function's minimum. Okay. Yeah, I don't think it is a known formula. 1.46, everyone keeps saying that. But still, what's the so this thing they're talking about is called the reflection formula.
Yeah, it's actually like the gamma of p times gamma of 1 minus p equals like I over sine.
What's the correct formula for the reflection?
Yeah, that is the.
Now we're talking. There it is.
Yeah, that's the
Pi.
right.
Oh,
That's the right.
pi and
form-
z. Yeah.
And that's the one that I saw.
Yeah,
That's
yeah.
Yeah, that's
There we go.
That is right.
Euler's reflection formula. This guy Euler was really pretty good at math.
Zeta of z equals zeta of 1 minus z.
Yes, and this function
That doesn't
Zeta
make
is-
doesn't make sense.
No?
Because like the Riemann zeta of -1
Yeah.
is -1/12,
Yeah.
and the zeta of 2 is pi squared over 6 is probably not -1. Oh, this is wrong. Wrong person.
Really?
Yeah, this is wrong.
Well, that's some other function. This xi function. I don't know
Yeah, it's
what
the
that is.
Riemann zeta function.
No, but this one is zeta. This one here, that's zeta. This thing is xi.
Yeah.
That's a different Greek
Oh,
letter.
xi?
Yeah.
I never heard of xi.
Yeah,
They
xi,
look
xi.
similar.
Yeah, it looks
Yeah, it's a
similar.
different
It's
function.
squiggly, but it has
Yeah.
an extra squiggle.
Cosine by z over 2. That's interesting.
Yeah,
I could keep this formula in my notebook.
it's great.
Yeah.
Maybe someday you'll work on the Riemann hypothesis.
Yeah, that would be cool.
Wouldn't that be great?
It would be cool if I could solve the Riemann
I know. I hope you will.
I hope
You
I
can tell me the answer.
I hope I can. It probably is true.
Seems like it is.
Yeah.
It does. I think I would agree with you.
Yeah. But maybe someday.
There's a very nice book about that you might like. Do you
Oh.
know, by a guy named Mazer. Barry Mazer. They have a very. I wonder if I have
Let
it
me
here.
write that. Can you
Yeah.
draw the Riemann zeta function for me?
Well, we can.
But maybe
For
you
just
can
for
write down
real
the name
numbers.
of the
Yeah,
book.
the book. You would like
Here.
this book.
Oh no, I run away.
First, let's just. We'll do it in a minute, but let's do this book by Mazer.
Then can I
And,
write down the formula?
Sure.
Because I really like that formula.
Okay. Mazer, it was, I think, about the Riemann hypothesis. Oh, what's the guy's name? Stein? It's really nice, and you would learn a lot from it. There it is. It's this book. It came out about a year or two
Oh,
ago.
it's talking about the sum of all the natural
Prime numbers and the Riemann hypothesis. I think you will love it.
I know.
It's-
I know a lot about how
That book.
everyone's always talking about how prime numbers relate to the Riemann.
Let me show you what it looks like inside. It has some really nice pictures.
Then can I
And,
write
I
them?
mean, just so you'll like focus on the Riemann hypothesis a little bit. Tells you about it a little. What are prime numbers? Okay, you know. And then does it have some diagrams? Yeah. I mean, you can see pretty sophisticated book, but I think, well, maybe. Oh, well, that's the end of the book. I think okay, I'm not sure if you'll like it yet. Okay, you wanted a graph of the zeta function?
No, I wanted to see that formula.
Back to do this?
Yeah,
Wanna look
where
at that
is
some
it?
more?
Let's see. Yay! Finally.
Oh, you want to write it down?
Let's see.
This
Yeah,
one? Or,
No,
or down there?
that one.
The
I-
Riemann
I
zeta
memorized
function
it.
is related to the gamma function.
Uh-huh.
Yeah.
Can you?
But
Isn't
I
that
can
interesting?
we can look it up on Wikipedia.
Um,
you don't have to write it
Yeah,
down.
you could.
You could.
I can send
I'm
it to you by
gonna do my-
email.
I'm gonna. Hey, wait! I want to do this.
You can do it.
Let's see.
That's right. Writing it down is better than
That's
looking
true.
it up.
That's true.
Let's see.
You want to?
I'm gonna
Oh, you
do
want to
my-
practice doing zeta?
Yeah.
Okay, watch. I'll show you. It's hard. I do it like this. So here, copy how I'm drawing it. Start at the top like this,
What?
and do a little
Isn't
like
it
that. Do a
Wait.
little of that, and then go down over here, and then there, and then around.
That's this one.
That's that. That's a zeta. So let's
It's
blow it
actually
up.
called the Riemann zeta function.
Right. But if that Greek letter zeta, if we blow it up, you can look at it carefully.
Now can you go back?
Yeah,
It
let's
doesn't
just
write
look
down
at
my
it
formula.
carefully.
Let's see.
Where is it?
There.
I've covered it. There. You can sort of see how to do it. Whoop, then over there, and then down. Whoop, over there, and then.
Then like then
Or just stare at it on the screen.
I'm just
You're gonna copy mine.
I'm just copying now.
Yeah, all right.
Yeah,
Like
this
that.
is kind of.
It's
not-
fun to write in Greek.
Uh-huh. Let me.
I'm not doing it that well. I'm gonna improve it from what I see on the screen. Little, and a big curve.
I'm just gonna copy you.
Oh, that's not so good. I think I need to improve my Greek.
Let's see it. Let me try doing that.
Gamma is much easier.
Let's
That's true.
Yeah, that's-
Zeta is one of the hardest Greek letters
is.
to
Yeah,
draw.
that's why I.
But it's important if you're going to solve the Riemann hypothesis, you have to be able to, well, you'll be typing it, I suppose. But
Here, here's a big.
that's it, like that. That's the big curve. And then just come around and go backwards a little. Yeah, like that.
Wow,
that's
good.
pretty good.
That's pretty good.
That's a good start, right. Exactly.
The zeta of. Can I use your pen? This
Yeah,
pencil's
sure.
kind of.
I can sharpen it. There's an electric sharpener.
It's kind of got broken. a bit.
All right.
This is a good pen.
Yeah. I might have an extra one if you want.
It's okay.
All right. I'll see if I have one. I have a professional mathematician pen.
Wow.
Here you go. I'll give you your
Wow,
It's a-
now you
it's
have
a
to
present.
save it.
Whoa.
Oh.
Okay.
Let me. Can I
What
just?
did you
So
say?
keep using mine for now.
Thank you.
Yeah. What would you call this? A professional mathematician?
Well, it's really just a pen,
Yeah.
but
It's just a pen that you.
but
have
it's
in-
Pilot Razor Point. It's a nice pen.
Let's see.
2 gamma of z. So
Yeah.
gamma almost looks like an upside down L, kind of.
Or just
Like that.
F without that little
Yes,
bit.
it's an F with missing part of it.
Gamma C divided by.
Make sure I'm not forgetting
Hey,
anything.
you
Oh yes, I thought I had a meeting.
Okay.
Okay.